We all learn the basic rules of biology and chemistry in school, right? But have you ever stopped to wonder if life, at its most fundamental level, actually plays by those rules? Or is something much stranger going on? Well, that's exactly the question we're diving into today. We're going to look at some pretty wild evidence suggesting that enzymes, these tiny machines that power our bodies, might be using a spooky trick to get their work done. A trick that seems to just totally break the laws of classical physics. Okay, so before we can talk about breaking the rules, we first got to understand what those rules are supposed to be. Let's start with the standard textbook picture of how these things are supposed to work. So, at their very core, enzymes are basically life's little accelerators. They're proteins that take chemical reactions that would be ridiculously slow and speed them up by millions, sometimes even trillions of times. I mean, without these things, digesting the lunch you just ate could literally take decades. No joke. The easiest way to think about this is to imagine any chemical reaction has to climb over a steep hill. This hill is the activation energy. Now, enzymes are just brilliant little engineers. They don't give the molecules a rocket pack to get over the hill. Nope. Instead, they just reshape the whole landscape. They lower the hill itself, making that journey from start to finish way, way easier and faster. So yeah, the classical rulebook seems pretty straightforward, right? You add some heat, molecules start zipping around faster, they collide with more energy, and boom, the reaction speeds up. For humans, that sweet spot is right around 37 degrees Celsius. But if you go too much higher, the enzyme literally falls apart and stops working. It all makes perfect sense, or at least that's what we thought. And this is where the story starts to get really weird. Scientists started running experiments, and the results, they just didn't line up with this nice, clean picture. The numbers they were getting they were just wrong. Like, wildly wrong. So, to really dig into these reactions, chemists use this super clever tool called the kinetic isotope effect, or KIE for short. The idea is pretty simple. You find a hydrogen atom that's involved in the reaction, and you swap it out for its heavier cousin, deuterium. And because deuterium is heavier, it's just plain harder to move around. So the thinking goes, the reaction should slow down by a nice, predictable amount that you can actually calculate with classical physics. But when they actually ran the experiments, the results were just jaw-dropping. Look at this. The prediction was a slowdown of maybe, 6 times. But for an enzyme from a soybean, the actual slowdown was 81 times. That isn't a small rounding error. That's the classical model completely falling apart. I mean, just let that sink in for a second. 81 times. That is so far off, it's like predicting a drive will take 6 minutes, and it actually takes almost an hour and a half. Clearly, something else, something not in that classical rulebook, has to be going on. So this huge discrepancy forced scientists to look for a really, really mind-bending explanation. And they found one in the bizarre world of quantum mechanics, the quantum tunneling hypothesis. See, the old model says you have to climb that energy hill. There's no other way. But quantum mechanics kind of just shrugs and asks, are you sure about that? What if there's a shortcut? Okay, so on the left, you've got the classical path. You go up and over the top. You need the energy, end of story. But on the right, that's the quantum path. A tiny particle, like a proton, doesn't even bother climbing. It just sort of disappears from one side and reappears on the other. It tunnels straight through the barrier. Now, in our everyday world, that is completely, totally impossible. And this isn't some wacky sci-fi idea. It's a serious scientific hypothesis. As scientists Klinman and Cohen put it, it's possible that evolution itself has been tweaking enzymes for billions of years to take advantage of this quantum shortcut. Life, it seems, might be a quantum mechanic. But hold on, the story doesn't quite end there. This idea of deep tunneling is amazing, but it seems to work best at super, super cold temperatures. So what about inside a warm, messy, living cell? Well, that's where a more recent and even more subtle theory comes into play. This new idea, which we call quantum transition state theory, suggests something else entirely. It says the quantum magic isn't about digging a tunnel through the bottom of the hill. It's all about what's happening at the very, very top. So let's break that down. Deep tunneling, on the one hand, is that full-on shortcut right through the barrier. But quantum transition state theory, or QTST, is a bit different. It says that because of quantum effects, the peak of that energy hill isn't a sharp point. It's fuzzy. It's spread out. and that makes it effectively lower and way easier to cross, even at the warm temperatures inside you and me. So that brings us to the million-dollar question, right? We've got two different quantum theories. Which one actually fits that crazy experimental data? Which one can explain that 81x slowdown? All right, and now for the moment of truth. Let's see what happens when we put this new theory to the test against the actual real-world data. And would you look at that? This is the big payoff right here. The little dots you see, those are the real, actual measurements from the lab, taken across a whole range of temperatures. And that solid line? That's not just some random curve. That is the precise prediction made by the quantum transition state theory. I mean, the match it's pretty much perfect. This is some seriously powerful evidence. And this isn't just some lucky fit either. The model works beautifully using just two key physical ideas: how the molecule's vibrating right before the reaction, and how fuzzy that energy peak is. And the best part? The numbers that make the model fit the data perfectly are the exact same numbers that fundamental quantum chemistry predicts they should be. It all just clicks into place. And it's not a one-trick pony either. The theory holds up again and again. Scientists tested different enzymes, they swapped in even heavier versions of hydrogen, and the model just kept on working, explaining all these different sets of data that were, frankly, totally baffling before. So, what's the takeaway here? It's pretty profound. Quantum effects are not just some weird footnote. They are absolutely critical for life as we know it. But it's not the dramatic, teleporting tunnel we first thought. It's something more subtle, a quantum fuzziness right at the peak of the reaction that gives life its incredible, surprising speed. This really changes how we have to think about biology. It's not just squishy stuff. It's deeply connected to the fundamental laws of physics. And it just makes you wonder, right? If life is using quantum tricks for something as basic as speeding up reactions, what other secrets is it hiding in plain sight? What about photosynthesis, or even our own consciousness? What other quantum magic is happening right under our noses?